Good morning. I'm Bill Gropp, the director of NCSA, and I'd like to welcome you to NCSA for today's colloquium by Gabriella Gonzalez. NCSA was founded to address the need for HPC in support of breakthrough science, with computational general relativity the driver behind our founding director, Larry Smarr's creation of the proposal that started not only NCSA, but then also started the National Science Foundation supercomputing centers. Today, NCSA is proud to be part of the LIGO consortium, and we're very proud of our contributions to the use of innovative high-performance computing in this new way to look at the universe. NCSA has had a long and productive partnership with the Astronomy department here at Illinois, including recent projects as the Dark Energy Survey and the Large Synoptic Survey Telescope. It's a very exciting project that we are partnering on. And we look forward to these and other collaborations. Here to introduce our speaker is Leslie Looney, the Department Chair of Astronomy.
Thanks, Bill. It's my great pleasure today to introduce Professor Gabriella Gonzalez. Astronomy, as Bill just said, Astronomy and NCSA have a long partnership together, and LIGO really represents that partnership in a fundamental way, bringing together really cutting-edge astronomy and computational techniques to really produce amazing and great science. It's a type of synergy that really exemplifies what we're really here to do, which is this fundamental change and shift of perspective that gives us a transformational science objective, like finding gravitational waves for the first time, opening a new window to the universe, which is what's really going on here today. We're here today alive, effectively when Galileo is first putting his eye to the telescope, and that is super exciting. Really part of our goal of the astronomy department is to seek out that type of new changing science, and it's really exciting to be part of that here today and listening to the results that we're going to have. Professor Gonzalez, she received her PhD at Syracuse in 1989, moving directly to an MIT LIGO staff sciences position, then accepting a faculty position at Penn State in 1997, then joined the faculty at Louisiana State University in 2001. She's been a member of the LIGO Science Collaboration since 1997, until just a few months ago was the spokesperson for LIGO Scientific Collaboration, beginning in 2011, where she was elected to that position, which is very prestigious. And she was there for the peak, right? She was there in early 2016 when the first announcement was made. And so I'm really glad to introduce her and hear more about that amazing discovery.
Thank you. It's very nice being here. Let me see if I can make this work. I can detect gravitational waves, but not always make computers work. I turned the internet off, so I don't get any Skype calls. Okay, so as it was mentioned, I want to talk about the birth of gravitational wave astronomy, which we say it was born on September 14, 2015, when we saw the first gravitational wave that I'll tell you about. But since then, we've seen quite a few more, and each one more exciting than the next. And let me first say that I'm talking for the LIGO Scientific Collaboration and the Virgo Collaboration, because this is a product of more than 1,000 people working for decades. And we'll keep working all together for more decades to keep improving on this. I'll give the briefest introduction to gravitational waves. You have much better experts than I am here in the audience. But this was a prediction from Einstein's theory in 1915 from the general theory of relativity. The general theory of relativity is very complicated. It's a nonlinear differential equation for space-time, how space-time, the grid of space-time, the four-dimensional space-time is determined by the metric of space-time. This is the metric that measures distances and times, and we combine derivatives of this metric in nonlinear ways in multiplications to form an Einstein tensor, and then we put matter and energy in the universe in a four-dimensional stress energy tensor, And then Einstein puts in an equation, one equal to the other, with the appropriate constants in front that have Newton's constant, because this is a theory of gravity, and the speed of light to the fourth power. That's a very unfortunate power, because it makes the facts very small, but that is the relativistic theory of gravity. So that's Einstein's equations. Again, all the complications are very hidden. It's a very complicated nonlinear theory. That's why solutions, there are very, very few analytical solutions, and the real solutions, the realistic solutions, need to use supercomputers like NCSA. But in vacuum, you can set this right-hand side equal to 0. You can say the metric is approximately the flat metric that we all use in the rest of physics, plus a small perturbation in this expression. This perturbation is dimensionless. It's a fractional change in distance. And then this equation becomes approximately a wave equation. And those are the gravitational waves. Einstein himself derived these in 1916 with a few mistakes in there, but the basic concept was there. There were gravitational waves as a solution to vacuum equations. Those gravitational waves are quadrupolar. They have two polarizations, one that transforms circles into ellipses that when you put them together, half a cycle apart, they form a plus sign. If you turn it 45 degrees, that's a cross sign. So those are the plus and cross polarizations of gravitational waves. So those are the gravitational waves, waves of space-time, solutions to an approximate wave equation in vacuum. How are they produced? That was a bit more difficult. They are produced by quadrupolar mass changing in time. So this is a mass quadrupole that sometimes we make introductory physics students calculate. For non-spherical mass distributions, one can calculate a mass quadrupole. And then if that mass quadrupole has enough time derivatives, then they produce this gravitational wave. So that is the source of the gravitational waves. It's mass quadrupoles changing in time. But again, this is where the constants come. And again, we have a g over c to the fourth. We have 1 over r, not 1 over r squared, because this is a field effect. We are not measuring power or energy. We are measuring the field. This is the gravitational field. So the effect goes down like 1 over r as the distance to the source. But still, in general, this is very, very small. So small that Einstein himself, when he published in 1916, he said, he put some constants in there, and he said, this will never be measured. And many people believe that for many decades. It would never be measured, just to put numbers in there. For example, in the 70s, the first binary pulsar was discovered. So these are very compact stars, neutron stars. And in this case, they were very close together. These neutron stars have the mass of the sun concentrated in the size of a city. So imagine that these are the densest stars in the universe, and they were so close that the orbit was only 8-hour period. So they were traveling very, very fast. They were producing gravitational waves, and that could be seen because the stars were getting closer and closer together. We expect that they, because of the emission of gravitational waves, they're going to get closer together until they merge at the end. The signal is going to be a chirp. It's going to be a sine wave, the sine wave from the periodic motion with twice the orbital frequency. And as they get closer together, just using Kepler's law, the frequency is going to get larger. The amplitude is going to get larger because they will be moving faster until they merge at the end. This is a chirp. So this is the maximum amplitude just before merger. How strong is that amplitude? And how often could this merger happen? This is what people began asking in the 70s when people were thinking about measuring gravitational waves. Well, how good a detector has to be and how often these things can be measured. These coalescences of binary neutron stars are estimated to happen in our galaxy once every 10,000 years, not in lifetime for an instrument. So one would have to make an instrument that's sensitive to signals that are much farther away. Let's say the Virgo cluster. In the Virgo cluster, these things happen about once every 50 years or so. That's more reasonable, especially given astronomical uncertainties. So how strong is the signal produced by a binary neutron star merger in the Virgo cluster? On Earth, when we put the distance in there and when we put all the numbers in there, that is 10 to the minus 21. The fractional change in distance is 10 to the minus 21. That means the distance between the sun and the Earth is going to change by about an atomic diameter. That's a very, very small change. However, in the 70s, people already said that perhaps that can be measured if we have interferometers. This is a quadrupolar motion. If we have interferometers, then we are measuring the difference in length between this and this. It's a null measurement. We can make these very sensitive. Can we really make them that sensitive? That was the question in the 70s. Well, that depends on how long you make them, because you usually are limited in the distance precision. So the longer you make your interferometer, then the better you are in measuring age. But you want to measure an age that would be 10 to the minus 21. That 10 to the minus 21 is, again, this merger of neutron stars in the Virgo cluster. So how long can you make this? Well, it depends on how much your agency gives money for and how good the technology is to work on long scales. It's very difficult to work this in long scales. So it was thought that maybe a few kilometers could work. Let me show you, however, I'll show you a lot of the progress that was made on the instrumental side, but let me show you, however, and apologize in advance, because I'm going to show a numerical simulation that is not from NCSA. I have beautiful movies from NCSA later on. But this one, if I can find my mouse. This one shows the challenge of numerical simulations. This is showing the space-time as distorted by two black holes before a fraction of a second before coalescence. And the challenge of these simulations is to calculate what happens near the black holes to see how they are getting closer together, but also showing how space-time is distorted far, far away from the system. Now, this part is easy because you can use post-Newtonian approximations, you can use perturbations, but as they get close, that was a mystery for decades. And it turns out that once they merge, there are crazy things happening near the black holes. This is again representing the curvature of space-time near the black holes. But at the merger, things look very simple. This was a surprise. Now it sounds natural. You have seen this many times, but thinking, I saw this happening. I saw this 10, 15 years ago. I saw drawings, schematics, when we were doodling on this and saying, well, we know what happens here. We know what happens here because once the two black holes merge in one, we know it's going to ring down. So we knew this ring down from approximations. We knew this part from approximations. This, we had no idea. And we all drew crazy things because crazy things happen near the black holes. And it was only from simulations with supercomputers that we can tell things are not so complicated for black holes. Neutron stars are another matter because there's matter in there, and matter is always more complicated than vacuum. But this is actually very good news for us because that means that if we have detectors that are sensitive enough, we know what to look for. We know what to look for, not only in this initial part and in this very short ring down, but also in the merger. So all these things were getting together. In the 90s, in the 70s, there were these designs that said if we build kilometer-long interferometers and if we make two of them, then we can have a sensitivity of about 10 to the minus 21. Actually, what was promised then, or what was estimated then, is that you could have noise of about 10 to the minus 21 which wouldn't let you see a signal of 10 to the minus 21. But in the time it took to build that, then it was estimated that technology would advance to install in the same observatories better technology that would be more sensitive. So this was a very, very long-term planning that I am not so used to seeing nowadays, but it did happen in NSF in the 90s. They did fund the construction of 2 observatories, 4 kilometers long on the side, one in Livingston, Louisiana, very close to where I live in Baton Rouge at LSU, and one in Hanford, Washington. This is in the middle of the desert, this is in the middle of the forest, so the geography is very different. They are 3,000 kilometers apart, that's 10 milliseconds in light travel time, and the idea was that you are looking for very, very small signals, so you need to validate the signal, seeing it in both at the same time. So this was built in the 90s. There was, like I said, an initial technology that was installed, began operating. We began operating detectors in the 2000s. They didn't have the sensitivity we wanted, but in 2005, we got that noise level of 10 to the minus 21. We operated it for a few years, getting better and better. In 2008, advanced LIGO was the technology for installing advanced LIGO detectors in these observatories was approved. Now, this was happening in the US, but there were other things happening in the rest of the world too. There was a UK-German project that was called GEO that before Germany reunification was going to be also kilometers long. Then budgets got a bit strained, so it got to be 600 meters long. But this has been a detector that has been used to develop a lot of the technology that we are using in advanced LIGO now. People from the GEO Collaboration and in the US and in the rest of the world had formed the LIGO Scientific Collaboration. Also in Europe, there was a collaboration that started as a French-Italian collaboration. Now it has several other countries. That's called Virgo. They built a 3-kilometer detector in Italy, and that was operating with its initial technology with LIGO between 2007 and 2010. So we had been working together before with a network of 3 detectors. And you probably know that we didn't see anything in those times. We only saw things for the first time in 2015. But there are 2 more in the works. There's a detector in Japan called Kagra in the Kamioka mine. That's a 3-kilometer detector, underground, cryogenic, that's getting built and commissioned as we speak. We think that this will come online around 2020 or so. And there's an observatory being built in India to house one of the LIGO detectors, and that will begin operating in 2024, 25 or so. So there are things happening all over the world, but what I'm going to tell you about is about things that happen in these 3 detectors. So this is the technology. This is actually my favorite topic. I will not have time to spend a lot of time on this, but I could spend hours talking about this. I told you that we use a simple Michelson interferometer. It's not quite true. What we do is we have a laser light from a high-power laser that was developed in part with Germany. High-powered because one of the limiting noises is counting statistics of photons in our photodetector. So the more photons we have, the smaller the relative uncertainty we have. That high-power laser travels in vacuum. This is high vacuum, 4 kilometers long, 1.2 meter diameter for the beam tube in a concrete enclosure. That's a person here. You can actually walk next to it, although you don't want to because it's dark and dirty, but you could. The mirrors are not mirrors bolted to optical tables. These are 40-kilogram fused silica mirrors with cutting-edge polishing and coating, dielectric coating for the mirror itself, hanging from fused silica fibers in a quadruple pendulum suspension. Why do we want pendulums? Because pendulums isolate seismic noise. You might remember from your introductory physics classes that if you have a pendulum and you move the suspension point very slowly, then the pendulum just moves along. If you move it at the right or wrong frequency, depending on your point of view, then the pendulum is going to move a lot. That's a resonance frequency. So we actually damp the motion at that frequency. But then if the suspension points move very fast above that resonance frequency, then the pendulum moves very little. So it isolates seismic noise above the pendulum frequency. And if you hang a pendulum from another pendulum from another pendulum, then that multiplies the isolation. That's not enough. The ground moves by microns sometimes, and we are talking about 10 to the minus 21 over 4 kilometers length. We are talking about 10 to the minus 18 meters. Now, I don't know that you carry units in your head. I didn't used to. But you might remember that 10 to the minus 10 meters is about an atom, that 10 to the minus 15 meters is a proton, and we are talking 10 to the minus 18 meters over 4 kilometers length. We are talking about a part in 1,000 of a proton diameter. So we are talking about measuring 10 to the minus 18 meter motion of this mirror with respect to this mirror over 4 kilometers when the ground is moving by microns. That's 10 to the minus 6 meters. So we need to isolate that motion quite a bit. And we do that not just with pendulums, but with active seismic isolation. We hang this pendulum from a huge system of layers of metals that have sensors that measure the size, the relative motion between these layers and cancel it. That's the active part of the seismic isolation. So here you have the pendulums hanging from this metal structure. All of that is in vacuum. And then all of that is multiplied many times because we have this quadruple pendulum here, and then we have another one here to make the light go back and forth about 100 times. We have an optical resonant cavity here. To do that, we need to control the mirrors so that the light going back and forth goes back and forth with constructive interference. So we need to control every little piece of metal in our detector so that the light has the right constructive or destructive interference as it's designed to work. So the control system, the engineering and the control system of these detectors is amazing. So we have Fabry-Perot cavities in the arms. We also have a power recycling cavity to have more circulating power. We have a signal recycling cavity. And all of that to have a little signal at the end that is noisy most of the time, but that's a gravitational wave signal in which we measure the noise. And if you thought that this was complicated enough, this is actually our simplified diagram. I'm not going to go through this. This is just to show the complexity, but this is what comes out of that. We have a photodiode. Actually, we have 2 photodiodes, and we add the signal of those 2 photodiodes, and we get this noisy signal at the end. This is what has an RMS in certain frequency of about 10 to the minus 22 now. And this is what we had in 2015. We decompose the noise in frequency to show how much noise we have at different frequencies. So this is 10 to the minus 21, 22, 23, and you can see that the lowest noise we have is between 100 and 200 hertz or so. And at that frequency, we have 10 to the minus 23. Then at lower frequencies, it goes up. That's because seismic noise and control noise that we need to get better at. At higher frequencies, it goes up because we are not using the highest power laser yet. We were using 20 watts. This is in 2015. We have 200 watts available. But even with those 20 watts, we already have 100 kilowatts circulating in here. So you have to take care of mirrors that are heating up and lensing. And so again, I can talk for hours about the experiment. But this is the noise. This is the noise that we have. And we didn't think this noise had a range in 2015. This noise had a range for detecting binary neutron stars at about 60 megaparsecs away. In initial LIGO, at our best in 2010, we had a reach to binary neutron stars of 20 megaparsecs. So this was already 3-4 times better. 3 times better. We got 70, 80 on good days. So it's not what we want. Actually, the optimal sensitivity that we think we can achieve is 200 megaparsec sensitivity. We can see binary neutron stars up to 200 megaparsecs away, or even farther away if they are oriented just right. But we thought we had actually had a plan before that we didn't need to wait until being perfect. We just needed to start when we were good enough. So we said when we get 3 times better in around 2015, we'll have a science run, we'll take data for a few months. We probably won't see anything because, again, for binary neutron stars, the predicted range was that we would have a few percent probability or less than a few percent probability of seeing a neutron star. But then we might put some limits on black hole theories, because black hole theories on how often there are binary black hole systems merging in the universe were all over the place. There were astronomers saying, black holes never meet each other. There's too few of them. They will never be in binary systems, and even less coalescing and producing gravitational waves. And other people said, oh, you should have seen those already. So we would at least be able to say something about those. As you know, on September 14, 2015, we saw for the first time gravitational waves from black holes. But just to show you what this looks in the control room, not the detection, but the interferometer in the control room, let me show you this movie. So this is showing the spectral sensitivity when the detector is not locked yet. This is the light. This is the light in the mirrors at the end. This is the X arm. This is the Y arm. This is the dark port at the output of the interferometer. This should be dark if we are at the right place. Here we control some of the cavities, and now we are aligning. Now you can see light in here, so we have light circulating in the arms. The cavities in the arms are locked. We have some sensitivity. This is a sensitivity I showed before of 10 to the minus 23. And now we are turning on knobs. People here, you don't see the people, but there are people doing this. They are turning knobs, aligning the interferometer. You see this getting dimmer. You get the sensitivity getting better. There's still some noise there, so now we have to turn on some low noise systems. And then this gets very dark, and that gets sensitive as we want. And now we try to keep it there as long as we can. A few times a week, there are earthquakes and things that take us out of luck, sometimes bad luck, sometimes a storm, so we are not on all the time. But this is what the control room looks like when we are taking data. What we look in the data is not just what we found, coalescing binary systems, but we look in the data for lots of different things. And we have been learning about how to find things in the data for a long time. So we know how to look for coalescing binary systems because we know the waveforms. We know how to look for continuous sources. Those would be produced by gravitational waves by rotating non-spherical stars. And pulsars, neutron stars in our galaxy, if they have enough non-spherical, if they have mountains that are large enough, if they have a quadrupole big enough, then they would produce periodic gravitational waves. You look for those differently than you look for these transient, these chirps. We look for generic transients without using any model. We use wavelet methods for that. And we look for a cosmic gravitational wave background, the kind that could be produced by the early universe, except that we think that that's too small for us to see. We look for any kind of stochastic background that could be produced by many unresolved sources. So we do have systems looking for all of these signals all the time. Some searches take longer than others, but we are looking at these things. Especially for these transients, these are continuous sources, these are transient sources. For these, we are looking online all the time. And it was because of those online methods, and it was the method, the algorithm that we were trying, looking for generic transients, the one that found found for the first time this signal on September 14 of 2015. And this is absolutely nothing like what we expected to show you for the first detection of gravitational waves. I'll show you how we actually look for the signals. It's not looking at signals, at waveforms like this, but this is the most beautiful image to me. This is a signal in blue, is the signal from the photodiode at Livingston with some minimal filtering and calibrated. So this is calibrated in strain. And this is what you usually see, which is noise. Again, there's some minimal filtering, so we are filtering the low frequency and high frequency noise on some lines. And this is noise again. But here we saw, for a fraction of a second, that there was something that looked like a sine wave growing in frequency and amplitude and then ringing down, quietly ringing down. The amazing thing was that we could see it in the time series. We never expected to see this in the time series. But also that in Hanford, 7 milliseconds later, if you do the same filtering, you see here some noise, but here you see the same thing. So this was a gravitational wave. It was so unexpectedly large, so unexpectedly clean, that none of us believed it the first day. We all thought this was too good to be true. We all thought that somebody had injected it, because we do tests like this all the time. We do push our mirrors simulating gravitational waves. We inject signals in the software, in the data all the time to test our analysis systems, to test our hardware. So we thought this was one of those. So we were looking for the person who did that without asking for permission. I was the one who was supposed to give permission for this. We were planning some blind tests, but we had not authorized the starting of those blind tests yet. It took a while, but we did confirm this was real. This was a gravitational wave, and it's not because it just looks beautiful like this. It's not because of this, which is probably the figure you might remember from our paper in February 11, 2016. This is, again, the signal in Hanford and Livingston. This is the comparison with a numerical relativity waveform or with a reconstructed waveform that we can have without assuming what's in there. This was so strong that without assumptions, you can reconstruct the waveform, and it looks like the numerical relativity waveform. You can subtract one from the other, and it looks just like noise. You can plot. This is one of our best diagnostic instruments for glitches, that is for transients that are not gravitational waves. We make a time-frequency diagram. This is time, this is frequency, and the power implies a normalized amplitude, a signal-to-noise ratio if you want. So bright is powerful, blue is normal noise, and you can see the chirp. You can see the signal getting brighter and higher frequency with time until it merges. And you see this in Hanford and this in Livingston. This is actually one of the things that, again, we never expected to see. We thought that the signal was going to be small enough that you wouldn't see it in the spectrograms. You had to dig it out of the noise. But here, there it was. What we actually do to find the signal and to estimate, to find this kind of signal and to estimate the parameters, is we do something called template matching or matched filtering. So we have some waveform that we think is in the data, and then we have a model for that waveform, and then we cross-correlate our model with the data without knowing whether there's something there or not. And if our model matches what is in the data, there will be a large value of this signal-to-noise ratio. But if there is no signal in the data, then there will be not 0, but a random number. So what we have to distinguish is how significant is this peak from the expectation of random numbers from the correlation of your template with noisy data. Now, this looks very clean. Unfortunately, when you do this with any template for any of the LIGO or Virgo detectors, you will see tons and tons of peaks like this. Some that have signal-to-noise ratio of thousands. And those are not gravitational waves. We know they are not because we don't see them in the two detectors. That's because we have lots and lots of transients in the data. Our data is very, very non-Gaussian. That's one of the many challenges we don't often talk about, but it is one of the main problems we have in doing analysis. So what we need to do is not just look for a peak for one model, but use many different models. We actually use thousands, tens of thousands. I think in the last count was 200,000 templates for binary coalescences, each template with different masses, different spins. And then we make sure that if we find a peak that looks significant with respect to what we expect, we make sure that we see a peak in the other LIGO detector within 10 milliseconds. We use a 20 millisecond window just to be sure. And that the same template is the one that produces the signal. So that's how we find the signals. It's not looking at that beautiful filtered waveform on the screen. We don't have graduate students looking at the screens all the time. We have graduate students looking at web pages that have numbers for these things. So this is a histogram that you should remember from that first paper that defines this is a detection. This is a histogram of the number of coincidences we have found in Hanford and Livingston. This is our loudest coincidence, which is what we call the detection. It had a signal-to-noise ratio combined between the two detectors of 23 or so. That was our loudest one. But we found tens of coincidences, other less loud coincidences. Those are all here. These are all less than 12 or so in SNR. So the question is, how often do you see these by chance? The way we measure that is we analyze the data in the two detectors. We look for these peaks in signal-to-noise ratio produced by the same templates, but we fake the time in one detector. Instead of using the true time, we use the true time plus 10 seconds. So any coincidence we find has a 10-second delay. That's not an astrophysical trigger. That's a random coincidence. So this histogram in black shows how many of those coincidences we found. Of course, it shows a number less than 1 because we did this millions of times, so we can measure, this is like the probability of finding that coincidence, and you see that we didn't see anything that loud. And that's why we call this a 5 sigma detection. This actually had, the way we like to say is that it had a probability of being a false alarm of 1 per 200,000 years or so. And it turned out that most of these things that we found in here were actually the signal in one detector with some random noise in the other detector. So if you take that signal out, if you snip out that fraction of a second, then this is a histogram that you get. So this is the proof that we have a detection. Now, what did we see? That's another question. To know what we saw, what were the masses, what were the distances, what are the parameters of the system that we saw, for that we need to find, to zoom in many templates with similar parameters and see which ones correlate better with the data. And there are many parameters for the templates. There are the two masses, the final mass and the final spin, the distance to the source, the inclination of the orbit, the position in the sky, and I'm not showing here, but we also have the spins, the individual spins, which you can find aligned to the orbit. You can define as aligned to the orbit or perpendicular to the angular momentum. And in each of these planes, you can plot or put a color dot for the cross correlation of that template with the data. And then in here, we draw a 50% contour and a 90% confidence contour. And then when we project on the axis, we say, well, the mass of this, the masses of these systems were 36 solar masses, plus minus a few, with 90% confidence. And this was, so this was 36, this was 29, plus minus a few more. So you can have not just estimates of the parameters, but errors. To do this, you need all these many waveforms. To get that many waveforms, you need not just the approximations, but you need to tune those approximations to actual simulations of gravitational waves. And that's, again, where computational physics and numerical relativity come in. These are not all templates generated by numerical relativity. That would take centuries, probably, of computer time. These are approximations, phenomenological approximations to the waveforms that have been validated with numerical simulations. Not every single one, but in general those. So it's not looking at this beautiful waveform, how we find the parameters is by doing all of this. Now that was the first detection, and that was exciting enough. But there were quite a few more. We took data, and we had decided that we were going to take data. Actually, we thought that we were going to take data for 2 or 3 months. We were going to stop before the holidays. But we were so excited about this first detection. And there was a candidate that was also matching something that looked like a signal, but in this false alarm rate, we calculated that this could be a false alarm once every couple of years. So for experimentalists like me, that's not quite enough. 2 sigma if you measure it, if you like sigmas. So we said, well, let's ask our people to work over the holidays, and let's take data until January, because we still don't have new hardware to install in January. We were planning, we needed a break, but we decided not to take the break. And that was very nice, because on December 26th, that was actually still December 25 in the US, so I call it my Christmas gift. We had another gravitational wave detected, again, 5 sigma detection from another binary black hole system. So we had 4 months of data. Those 4 months of data, we had about 45 days when we have the 2 detectors working in a good state. And in that time, we had 2.5, depending on how you count, detections. This is, again, the histogram I was showing you. This was the first detection. This is the second detection, very significant with respect to the background, especially after you subtract this first one. That's that candidate. That's our 3rd loudest trigger, but not quite. Not quite a detection for our standards. If you plot the waveforms of those, not the reconstructed waveforms, but the templates, then this one is the largest amplitude, this one is the longest, this one is almost a second in the data. Now this one, it has a much smaller amplitude, not just smaller SNR, but smaller amplitude because it's smaller masses, so you don't see it in the data. So the similar plot to that figure that we all loved in the first detection paper doesn't look as nice when you look at the filter time series. This is a filter time series over 1 second of data. And I have to draw for you the template that we found in there, because if not, you don't see it. For the first detection, I didn't even have to put a template on top of the data. But here I have to. It's not visible. However, it is a very large signal-to-noise ratio, especially at Hanford, which was a more sensitive detector at the time. And you can kind of see it there, but maybe. But again, this is not how we look for the data. This is what we do. That's a detection. The parameter estimation is a much more difficult one. However, we also do, or like to do, these are not visualizations, but music. I call it gravity's music. What we can do is put these frequencies, which are in the 100 hertz. You saw that our best sensitive band was in the 100 hertz. The coalescing frequencies of the first black hole was at about 200 hertz. The second black hole binary system was at 250 hertz. So that's in the audible regime. So we like to put this on a speaker, the digitized signal on a speaker, and this is what you hear. That's a longer signal. That's a shorter signal. Now, that's probably not what you were expecting. How many of you have heard the chirp on YouTube? Was this the one you heard? No, it wasn't. And that's because we learned from astronomers. You know, in astronomy, you see all these beautiful pictures of the infrared and the ultraviolet with beautiful colors that are not real because they're not in the visible spectrum. They are using false colors. So we just did the same with sound, and we increased the pitch. We just added 400 hertz. And now it sounds a lot nicer. But the first one was a real one. Now you know. Now this is astronomy. Of course, this was testing. We were in the paper saying Einstein was right. This is another proof of Einstein's theory. That's not why we build these instruments. We build these instruments as observatories. Of course, we can test again theory of relativity and the theory passed. I wouldn't say with flying colors because the precision tests that we can have are not as precise as the ones you can do with pulsar timing and other, or time delays or things like that. But it is a different kind of test, and it all was good. But we are now doing astronomy. Everything we knew about stellar mass black holes was from X-ray astronomy. You cannot see the light of a black hole because it's black, but you can see light if there are X-rays being emitted in jets from matter that's around in the magnetic fields, or whether there is a companion, a stellar companion that is emitting light. So you can see black holes. These are called X-ray black holes, even though it's not the black hole itself that emits the X-rays. And we knew masses. We didn't know any binary systems because they were in binaries, but with regular stars. And they were all less than 15, 16 solar masses. That's all we knew about black holes. And this is, of course, a very hot and very active topic in astronomy. These are our black holes. This was the one in September 14. It's still the largest we've seen. The final mass was 60 solar masses, and even the initial masses were larger, significantly larger than all the ones we saw. This was 1226. This one was more normal, even though this final mass was still larger than all these others. And then I'm going to tell you that we saw 2 more black holes in our second observing run, and this is our candidate. So we are building a census of black holes, and not just of the masses, but kind of location and spins and properties. And the more sensitive we get, the better this will be. So we took the 1801, we had those 2 detections, maybe another, I should have put another dash line in there. We had a sensitivity between 65 and 80 megaparsecs, 2 binary neutron star mergers. We took some time down to work on the detectors. Again, I told you that we can make these detectors, we will make these detectors work perhaps as good as 200 megaparsecs, so we still have a lot of work to do. So we took some time down. In November 30th, we started taking data again. We actually made one of our detectors a bit worse, 60 megaparsecs, but another quite a bit better, 100 megaparsecs. The Livingston detector was better. Here, the Hanford detector was a better one. And on January 4th, we saw a signal that was also from 2 black holes. We said, oh, well, another black hole. All news. But it was very exciting because we knew that Virgo was working very hard to join us. They joined us on January 1st and on August 1st, And on August 14, we saw our fourth signal of black holes, but now with 3 detectors. And that made it a lot better because now you can triangulate. Now you can see the signal to noise ratios are quite different. This is the one in Livingston that now it's the best working detector, or it was in '02. Excuse me. So that is the brightest signal. This is Hanford, this is Virgo. It looks like a small signal. In fact, you wouldn't believe it if it was this one alone. You would believe it if it was this one and that one, if it was this one and this one, maybe. But it was only obvious in the time series in Livingston, not so obvious in Hanford or Virgo. But now you can tell more about parameters. Not just about the localization, which is much better localized, but we could also tell about the polarization of the signals, and we could also tell about the spins. We have been trying to measure the spins of the black holes before merger. Turns out to be quite difficult. The waveforms are very short, and they don't change as much because of the spin, so our measurements are not very good. But it turns out that for this one, we could more or less tell that if you measured the spins of the black holes before merger projected along the axis of the orbital of the angular momentum, the orbit angular momentum, then it was close to 0, which is strange because it means that the spins are either small or anti-aligned, but it had a negative value. It was probably negative. So that meant that the spins of the black holes were either not aligned with the orbit, and if they were, they had negative, effective negative alignment. So it made for these beautiful images of black holes spinning in weird ways. I'm waiting to have stronger signals to be able to tell more about spins, but these observations of spins are very intriguing. Now, let me show you the publications of the gravitational waves. This was the first one in 2016, signed by the LIGO Scientific Collaboration and the Virgo Collaboration. For the second one, we already gave it a name in the title. This was a smaller mass, so we put the mass in the title. For the next one, this was the highest mass we had. Not the highest mass, but the largest distance. This had a redshift of 0.1, very close in astronomical standard. This was 0.2. The last one was a 3 detector observation. So every title changes a bit depending on what we see different in these detectors. Another pattern that you see is that they are all signed by both collaborations, which are huge collaborations. This is just the logos of the LIGO Scientific Collaboration that includes NCSA. But we all work together for doing this. Now, these were the black hole signals that we had detected. And I didn't put the time scale in here, but these are the templates for those. You see, this was the largest amplitude, this was the longest, but it was just about the second in data. And on August 17, just 3 days after we saw this, and a few days before we had decided to shut down, we were going to finish this observing run on August 25, because we had hardware to install. We saw the first observation from a binary neutron star coalescence. And this is a beautiful visualization by NCSA, of a neutron star coalescence. With neutron stars, you don't have just horizons of the black holes. You have all this space-time. This is just a distortion of the space-time, but it shows how much it's changing and in many complicated ways. And of course, the signal is quite a bit longer. It doesn't last a couple of seconds. Notice how these are shrinking now. It's a lot smaller in amplitude, but it keeps going and going, and it's going to take a while. I guess the two movies didn't work that well together. There. It keeps going. But now you can hear it. We all run out of things to say while this is happening, but I love putting the movie because it's so colorful. So that was the last 50 seconds, but this signal spent 100 seconds in band. That was too long for a talk, but 100 seconds. Now, I cannot play for you the data itself, even if I add a frequency to, because it's very small. Even here, it's smaller than any of the other ones we saw. It's much, much smaller than the noise. We can pick it out because we can match the template for this long a time. So we have a huge signal-to-noise ratio. This is the largest signal-to-noise ratio detection we have, but the smallest amplitude. So this was a neutron from the masses, from the templates. We could say these were two small stars, small as neutron stars. These were probably not black holes. Not only we could see the gravitational waves, but because we had practiced sending these alerts to our astronomy partners all over the world, we did do that with this one. We had done that with the black holes, and there had been no confident observation of an electromagnetic counterpart, and none was expected because these were binary black holes. But for this one, we could expect one. We expected one if this happened to produce a GRV that was beamed to us, but that would only happen about 10 or 20% of the time, so we weren't sure, but people began seeing things. We ended up publishing a paper, and you notice that this paper, just like the others, is signed by the LIGO Scientific and the Virgo Collaboration. This one is the list of collaborations in this paper, not the list of authors. Here we already have 1,000 authors. Here we have 3,600 authors. This is not just from LIGO and Virgo, but all the electromagnetic collaborations that went out looking for this data. So this is what we looked in what we found in the gravitational wave spectrum. Very nice and strong in Livingston. Not so nice, not so strong because Hanford is not as sensitive. Not quite there in Virgo. It turns out that we knew that Virgo had sensitivity to see this signal. The fact that it didn't meant that it was in a blind spot for Virgo, and that is better information for localization. We could tell about the masses, and the masses are small. This is what makes us call this neutron star coalescence. Not everything is so clean. Let me go because I'm going over time, but you can ask me about that later. But that was a gravitational wave observation. 2 seconds after the gravitational wave observation, there was a gamma ray trigger. A gamma ray trigger seen in 2 different bands in Fermi GBM and by integral on, again, a different band. I don't know what that is about. So this is what proved, fine. This is what proved the connection between gamma ray bursts, short gamma ray bursts, this was a 2-second gamma ray burst, and gravitational waves, mergers of neutron stars. Okay. We had been waiting for this confirmation for a long time. However, this was not a very strong gamma ray burst. And from our observation, this signal we had a distance estimate of about 40 megaparsecs. That's very, very close. So that meant that we were not seeing this phase on. So that meant that we were looking for interesting other electromagnetic confirmation, and there was. This is all due to the localization we could do. The localization of the Fermi GBM trigger, because it wasn't so Fermi GBM doesn't have such good localization, and it was not that sensitive at the time. It was a huge patch in the sky. If we had only had the LIGO detectors, we would only be able to say that it's either there or there. But because we had Virgo in there, we could say it's somewhere in there, which is still a large region, but not that large. And because it was kind of close, 40 megaparsecs, astronomers went out looking for things in galaxies that were about that close. And they found it. So in NGC 499, I think, and this is that galaxy. And there is a spot there, first seen by the SWAP collaboration. That's a spot, a bright spot, seen 12 hours after our trigger, just as soon as it was dark in Chile, so that they could look at this galaxy. And that was the same spot 20 days before. That was the last time an image of this galaxy had been there. And it wasn't there. Everything else was there, but not that. So this is the galaxy where this happened, and that is exactly where it happened. And we know that because we have optical confirmation from many different observatories. Now these are 6 of the 20 different images that are from optical telescopes. But we have looked at this not just in gravitational waves and gamma rays like I showed you before, but in the optical, not just in the beginning, but then again later on. First it was blue, then it was red shifted. It was seen in the infrared. These dots indicate when there were observations, and these were when there were detections of transients at those. So there were transients in the infrared, one not so big in the beginning, and then one much larger in the end. There are signals in radio that were there for weeks. Those were the last ones, and there were signals in X-rays seen by Chandra. So this is truly a multi-messenger observation. Look at the list of messengers we have in here. We even have neutrino collaborations as authors of this, but there were no neutrinos seen in coincidence. But we did look even in that band. So there's a lot to say about that. This is astronomy. That's not my expertise, not my forte, so I will leave this for other astronomy colloquia to say, but let me just give you a glimpse of the future. We were at 100 megaparsec sensitivity with the LIGO detectors in this run. Virgo had 25 megaparsec sensitivity. Both of these detectors can be quite a bit better than 150. So we can increase our range quite a bit. And this is the plan we had even before we started taking data. We thought we would be here, and we were here in 2015, 2016. We planned to be here probably maybe not 2018, but maybe late 2018 or 2019. But this is where we are going. And this is where Virgo is going. So we are going to be seeing more and better detections. These things are coming. This is our plan. As I mentioned, we took data in 01 and 02, but we plan to take data in 03. This is probably going to be moved a bit in here. Things are going slow, but we plan to have about 150 megaparsec sensitivity. 200 megaparsecs is the target. So this is all coming for LIGO and Virgo. We are going to be filling this catalog not just with black holes, but now with neutron stars. This is our first neutron star detection. These are all the other neutron stars. As I told you, there are more detectors coming on, so we will have a network of detectors, all with about the same sensitivity. We are going to get better and better localization. This is the localization of those black hole observations. This was the first black hole observation. This was the first black hole observations with 3 detectors. This was the observation of that neutron star. This is what 3 detectors can do. 4 and 5 detectors can do even better. And we have ways of making sensitivities better. If we make these detectors longer, 10 kilometers, 40 kilometers, if we put them underground, if we make them cryogenic, if we make them use squeezed states of lights instead of just the coherent laser that we use, we can get 10 times better sensitivity. This will take decades and funding and promise, but it's all coming, not just in our gravitational wave band, but also longer periods with space detectors, pulsar timing, and cosmic microwave background, which I don't have time to do, but I'm hoping that you will hear about these with detections in the next decade or so, perhaps even sooner. Thank you.
So you said that it wasn't so much about showing that Einstein was right or any of those things, but the actual merger of the black holes, what other handles do we have about gravity in this extreme regime where you're probing the horizon?
We don't, so this was a qualitatively different test of GR, and that was great. I don't think NSF would have or should have funded if that was the only objective. But we will have much, much better tests of relativity with better sensitivity. We will have even, I didn't talk about that, but with this neutron star merger and the localization of the galaxy, we can even have cosmological tests. We can measure the Hubble constant independently of other methods like cosmic ladder or Cepheids. So completely independent, we can have cosmological measurements. We can do much better. However, for tests of general relativity in the high energy regime for black holes, LISA is the best bet. There you will have signal to noise ratios of hundreds. You will have black holes of million solar masses. And those are going to be the best tests of GR, in my opinion.
I'm amazed by the prospect of seeing gravitational waves from almost but not quite spherical neutron stars. I don't know if, but I've heard that there will be, they observe star quakes on pulsars so that they change periods, and so they must be doing something non-spherical when that's happening. I don't know. Do you have much hope of seeing one and seeing this kind of thing in the next few years, of catching neutron stars this way?
I do, actually. There are some bets going on whether our next new source will be a neutron star black hole or a pulsar or a continuous wave. Neutron stars are known to be very, very spherical. They have mountains that are a part in a million of a 10 kilometer, 30 kilometer scale. So they are very, very spherical. But we are getting more and more sensitive, and especially when we begin taking data for a long time, if the star is close enough, we should see it. We have now the best limits on some of the closest stars. We have the best upper limits on sphericity and emission of gravitational waves, better than radio signals from Vela and from Crab and from most of the young pulsars in our band.
I was wondering, with all the new technology that was developed for LIGO with lasers and mirrors and so on, has any of that made it into other uses in industry or in other sectors?
Yes, we have a list of those. It's difficult. It's always difficult to find a direct relationship. But for example, Lightwave was a company that made the lasers for the initial LIGO system, and they became a very successful laser company later on. The company that made our seismic isolation for advanced LIGO has then used it for other, not experiments, but other semiconductor industry. So we have pushed the edge, and that takes years sometimes into percolating into the rest of the industry, but it has, yes.
So what is the biggest challenge that you think LIGO will face in the next few years?
Getting enough sleep. we are working very hard, in fact, day and night. If you look at our electronic logs, you can actually log in the electronic logs of both, well, actually all three Virgo, LIGO, Virgo, Hanford, and Livingston observatories and see what people are doing. It's difficult to interpret because it's full of jargon, but you see entries at all hours of day and night working on improving the sensitivity. If you ask me what's the biggest challenge, I think it's keep going on this for the 10 years, the next 20 years, and then being able to stop to improve the instrument and take data. I think that tension will be more difficult. Once we begin seeing more signals, nobody will want to stop. But then you know that if you make it 20% better, you'll see 60% more signals. so there is that tension. When do we stop? That, I think, is going to be the most human challenge.
You said that the first time you got the signal, you didn't believe it. When was the moment that you realized you were in the Galileo's league?
It was a process. We knew we had an interesting candidate just as soon as we learned this was not a planned injection, which was a few hours. I mean, within a day, we knew this was not a planned injection. Then we had to worry about whether this was a hacking, and we did look very hard on whether somebody could have hacked the systems and inject something in there. We ruled that out, of course not 100%, but you would have had to have alien help or something like that to get it done right. But it was making sure that this was not due to anything else. We began looking at everything that could have produced a random coincidence. Something that, for example, we found out that within minutes, probably within seconds of the signal that we saw, there was a lightning in Burkina Faso that was the largest lightning ever recorded. So we began thinking, is this a coincidence? I mean, we concluded it was a random coincidence. We concluded it could not have caused the signal in our detectors because we have lots of sensors in our detectors. But getting that kind of confidence took months. And estimating the parameters, actually. We thought that we had everything in place to get parameter estimations within weeks. It took us months to review all the codes and the results on the analysis until we could tell not just parameters, but errors on those parameters and be ready to publish.
So I think you've made it clear you're going to map the next 10 years of black holes. Do you have some feeling?
And neutron stars.
And neutron stars and maybe pulsars. Do you have a feeling of could this lead to some new fundamental understanding of the universe?
Yes. Of course, we could, for example, it could be that once we have more precision, then the waveforms, the reconstructed waveforms, don't look like the numerical relativity waveforms. That is a test of relativity that would be telling you there's something wrong with relativity. That is something very new we would learn. My hope is that we will detect transients that we have no model for. That we will see a coincidence, and maybe not once, but more than once, that is as strong as the first one. If we had seen that first signal that was clear in the time series, it was 10 milliseconds apart in the two detectors 3,000 kilometers away, but it didn't look like a coalescence, it probably would have taken us more months to convince everybody that it was a gravitational wave, but we would have had to say, this is a gravitational wave. We don't know what produced it, but it is a gravitational wave. That, I think, will be coming too.
Thank you.
Thank you.